Last time we tried to argue that this raising and lowering operators for angular momentum operator, L plus and L minus, could be derived from this commutation relations between Lz and L plus or Lz and L minus, and these two are the derivations to show that the states L plus acting on Ln is an eigenstate of Lz with the eigenvalue n plus 1 times h bar, which is 1 h bar more compared to the original state. And likewise, this L minus acting on Ln is also an eigenstate of Lz, but with 1 h bar less compared to m h bar, which defines this lowering operator for L minus and raising operator for L plus. You could take the elevator, go either up floor or downstairs. Okay, so this is the power of this angular momentum raising and lowering operators, which will be used later. But what is the exact relation between those two? I only tell you that this L plus acting on Ln is the eigenstate of Lz with, say, n plus 1 or 1 h bar more, but this is just some kind of a semi-quantitative statement which says that this state, L plus acting on Ln, is actually proportional to Ln plus 1 state, right? But what is the prefactor or proportionality? C plus and also C minus. Okay, so we need to figure that out. What is this? It's not equal to this L n plus 1 or n minus 1, but with the prefactor C plus or C minus. So we need to find out what these prefactors are. So let's just figure that out. Remember, this Dirac-Bras state, which is L plus Ln C plus start. Remember, when we take the Hermitian conjugate of these two equations, we get this C star plus or minus. And we can take advantage of this Hermitian conjugate version of this eigenvalue equation. We can actually do this. C plus Ln C plus star Ln, which is L plus Ln L plus Ln. So if I simply just put this Dirac-Bras state on the left and Dirac-Katz state on the right, but Bras and Katz state are the same thing. Both are this L plus acting on Ln, but when I put it on the left, remember I need to really flip the order between these two. This will be minus plus Ln. What is this L minus acting on this Ln to the left? Well, this is nothing but Ln plus 1 times the C star plus. And that is precisely this one. And on the right-hand side, the Katz state is actually C plus. So C plus times C plus star is actually square of the C plus. This is square of C plus. But if you look at this part of identity, and you get L minus on the left and L plus on the right in the middle, between this Lm state, we could rewrite this L minus L plus in terms of L square and Lz. Remember that. Okay, so we already proved this identity last time. L minus L plus is the same as L square minus Lz squared minus h bar Lz. So let's just perform this eigenvalue calculation. So this is L plus 1 minus m squared minus m times h bar squared. That's it. Because Lm is the simultaneous eigenstate of Lz and L squared. We simply just plug in these eigenvalues that we assumed in the very beginning, and this will be the final result. If I simply just merge this Dirac-Brown-Cass state of the same stuff, and I will get this thing. But of course, we know that this is also normalized to 1 because the Dirac-Brown state Ln plus 1 and Cass state Ln plus 1. So this is the same thing, so this is 1. Which means immediately that this number right here is just C plus absolute value squared. So we're done. Okay, so C plus is found in the square root of this bracket, which is this stuff. And likewise, we could figure out the C minus coefficient in the same way that we simply just reverse the order between L plus and L minus right here so that we could get the C minus square. The C minus is, take this value. Of course, you don't need to memorize those coefficients. If needed, you will derive this. Okay, don't memorize this, but derive them. My advice. Next, we will actually argue and find the relation between M and L and what are the possible values for M and for L, their relation. Yeah, so let's take a short break. When we come back, we will address these two questions. That's what are the relation between M and L, what are the possible values, whether they are integers or half integers or non-integers. We could figure that out. So by now, I hope you're already familiar with this kind of a Hermitian conjugate and the definition of the Hermitian conjugate states or operator. Get familiarized with the Dirac notation. That's your job. So let's take a short break. 这里呢，需要大家熟悉一下这个狄拉克的符号啊，尤其是Hermitian conjugate 那部分啊，一个 Cass state 做了一个conjugate 之后就变成 Brown state， 那你需要把这个 Cass state 所有的里面的内容都交换交换它的位置。如果这个 Cass state 是一个 operator 已经作用到另外一个 Cass state 的话，那你必须要把 Cass state 变成 Brown state， 那这个 operator 要搬到 Cass state 的另外一边取它的 Hermitian conjugate。那这个动作呢，希望大家都能够了解是什么意思，同时也都能熟悉它的运算。那这是我们量子力学最重要的一个数学的运算的方式这个熟悉之后，那各位对这些更复杂的量子力学的计算也就能够轻而易举的可以掌握了所以我们说量子力学就是在学这些东西定义 operator 定义它的这个 state， 那你去把 operator 作用到这些 state， 看你会得到什么样的结果。用 Dirac 的 Brown-Cass 的这个 notation 可以把所有的这些可能的 eigenstate 都得出来这就是量子力学的一个最重要的数学的计算。So let's figure out the relations between M and L and also the possible values of. To see this, we need to go back to this identity or inequality here. That suppose I simply just put this two states together. One is the Dirac-Cass state and another is Dirac-Brown state, but this kind of Brown state are made of the same thing, which is L plus or minus acting on Ln. By now, you should be very familiar with this kind of strategy. And we know that this is something square, right? Because this is a Dirac-Cass state, which I call this psi-Cass state. But on the left, this is the Dirac-Brown state, which is the same stuff. But we simply just take this complex conjugation of this Dirac-Cass state, and this Cass state becomes the Brown state. So if you put this Brown-Cass state together in the inner product, this is something square. This is psi square. Just like the square of the Schrödinger wave function, but we do not intend to actually project this state, arbitrary state, onto any eigenbasis, but this is just the square of this Dirac state. Of course, the square of the Dirac state is always positively equal to 0, and we see consequence of the statement because now we can actually move around this operators, especially this L plus minus on the left or Dirac-Bras state here, could be moved in the middle to the middle, so that when we do so, this L plus becomes L minus and L minus becomes L plus. You see this? Okay? So now this middle operators becomes the product between L minus L plus or L plus L minus. Okay, so now you could actually change this product and replace this product by this L square and LZ and LZ square, which is this stuff right here. And then we simply just evaluate this matrix element, and this is the easy thing to do because Ln is a simultaneous eigenvalue of L square Lz. You simply just collect the eigenvalues that we defined earlier. These are the eigenvalues or the matrix element. Of course, this thing that in the bracket times h bar square must be greater than or equal to 0. This is from this conclusion that we have. This inequality really tells us the relation between M and L, which means that both minus and plus sign of this inequality should be satisfied. So let's do it one by one. So this means that LL plus 1 must be greater than or equal to M times M plus 1 or M times M minus 1. We need to simultaneously satisfy these two conditions, and let's solve this two inequalities, which could be easily done because we argued previously that L could be always positive. If L is actually more negative than minus 1, then we could actually flip the sign of L to L prime. Remember that. So that L times L plus 1 is always positive. L prime times L prime plus 1. Okay, so we can always assign the positive value to L or 0. So in that case, these two conditions tell us that M must be between plus L and minus L. The extreme values of M could be plus or minus L. So you can solve these two inequalities, use this condition that L must be greater than or equal to 0, and you immediately get this conclusion that must fall into this range between plus and minus L. And this is part of the reason why we choose this eigenvalue for L squared to be L times L plus 1 h bar squared. Okay, remember that we didn't mention the reason why we assume this eigenvalue for L squared. So now this is the reason. Because if the eigenvalue for L squared is simply L times L plus 1, then from this inequality we can easily solve this. Okay, the solution of this two condition is that M fall into that range between plus and minus L, which is really simple. And this justifies why we assume this eigenvalue for L squared is taken to be L times L plus 1 h bar squared. So let's just continue. Suppose the minimum value of n is called M minima. Then immediately we see that when we apply L minus to this state, L M minima, it vanishes, right? Which means that you have many different levels labeled by this quantum number L. M could be either one of them, ranging from minus L to plus L. But what is the value, possible value of L? We don't know that. We only know that L can be real number. We know very well that this minimum value of n exists, which is what? Minus L. Of course, the maximum value of n is actually m max. Suppose we simply would like to go to the basement. So this is our ground state, right? It's minus L stays the ground state. So there is no basement to go, which means that suppose we apply this L minus on this minima of the ground state, we cannot go to minus 1. Okay? Which immediately tells us that the C minus L and minima is 0, and minima is actually minus L. So likewise, and maximum is actually L. Okay, so now we get a more complete picture because we know that how many floors are there. So 2L plus 1 levels. So there are 2L plus 1 levels. M could be any one of them. So we could actually assign the minimum value of M to be minus L. And the next one will be minus L plus 1. Go all the way to the top level. And this is L minus 1 and L. Okay, so which means that we could go from the bottom to the top by repeatedly applying this L plus from the ground floor, which is minus L, and then go all the way to the top floor, which is plus L. And as a result, there are 2L plus 1 states. M could be any one of them. So which means that this 2L plus 1 is an integer because they are exactly 2L plus 1 levels, and of course this 2L plus 1 should be integer, okay, because we can count how many floors are there, 1, 2, 3 until the top floor. As a result, this 2L plus 1 could only be an integer, which means that L could be either half integer or integer. Because 2L plus 1 is an integer, and L could be either half integer. Half integer times 2 is an integer plus 1 is another integer. But integer times 2 is integer plus 1 is another integer. L could be either half integer or integer. We'll see in the future chapter when we talk about the spin, this situation where L equals half integer, for example, this 1/2 or 3/2 and so on, we could define this spin quantum number. In other words, the spin is a particular type of the angular momentum, and the spin operator is the same as angular momentum operator. It's just that we have two possible values for the electron for a single spin 1/2 particle. For example, the electron spin takes this plus or minus 1/2 h bar as the possible angular momentum. This corresponds to, for example, the spin 1/2 particle, which takes plus minus 1/2 h bar as the eigenvalues for the spin operator. But for L equals integer, we know very well that this corresponds to the orbital angular momentum. For orbital angular momentum operator, the eigenvalues are integers. So we will come back to this when we talk about the spin. But remember that from this general derivation, we know that L could be either half integer or integer. So now you know what this possible values for n, because it depends on whether L equals half integer or integer. For L equals integer, n could be what, like minus L, which is integer, all the way to L. But if L is actually half integer, for example, n could be what, suppose L is actually 1/2, n could be minus 1/2 or plus 1/2. If L is actually 3/2, n could be what, minus 3/2, minus 1/2, plus 1/2, and plus 3/2, and so on. The first case corresponds to the orbital angular momentum, and the second to the spin angular momentum. Later, we can actually add this 2 as a total angular momentum, which is L plus S. Remember, L describes the orbital angular momentum operator, and the S for the spin. The eigenvalue for L is actually integer. For spin is half integer. And so the total angular momentum is nothing but the sum over these two parts of the angular momentum operators. In atomic physics or in solid state physics, we can actually see whether these atoms carry magnetic moments by calculating this total angular momentum J and see what is the residual, say, spin moment and the angular momentum states, and so on and so forth. This is a very elegant way to argue and to derive all these eigenvalues for orbital angular momentum, or L. So in the following, we will change variables from this Cartesian XYZ coordinate to the spherical coordinate, as we already pointed out that in many potential problems, such as the hydrogen atom or this central force potential, we need to describe everything in spherical coordinate. In other words, we need to rewrite this angular momentum operator in the spherical variables, such as the radius, vector r, theta, and phi. So let's take a short break, and when we come back, we will simply just write down this, this expression for angular momentum operator in spherical variables. 从这边的推导可以连接各位在高中的时候读的理化为什么这些周期表里面的原子它是处于某一个角动量，那这些来源呢其实就是这里。当然我们还没有把这些轨道角动量跟自旋角动量加在一起如果我们加在一起的时候，就是各位在高中理化的时候读过的这些电子组态electronic configuration come from exactly this S 轨域S orbital, P orbital, D orbital, F orbital, and so on. All these different names of these orbitals come exactly from this total angular momentum J. You can actually go back to your high school textbooks or even general physics, general chemistry. You should understand this right now. Yeah.
最后一个那个黑板可以讲一次吗？就是 J 等于 L 加 S。
我们刚刚说到有两种不同的角动量嘛，一种是轨道的，一种是自旋。那轨道当然就是你 particle 围绕着一个类似轨道但是量子力学并不是真的如同波尔一样是一个轨道它只是用来说明，可以用古典的方式去大概理解什么是 orbital angular momentum， 就是一个 electron 围绕着 nuclear core 所能够携带的角动量那另外一种就是 spin 电子的自旋，各位在近代物理跟甚至普通物理都学过那它带的角动量就是正负2/4 h bar。那原因就是实验的原因。为什么电子携带一半的 h bar 的角动量呢？那我们理论并不能说明，我们不知道为什么，我们只能知道这就是电子它自己intrinsic 等于说自己产生的类似自己在旋转的这种角动量但是电子真的在自己在自转吗 ？No, this is also confusing, misleading picture. 电子并没有自己在旋转只是说电子除了轨道角动量之外，它必须携带一个它自己本身就携带的一种角动量，那它是正负2/4 h bar， 也就是 L 等于半整数。当我们把这两种角动量加在一起的时候，就是属于这个原子或者这个电子的 total 的角动量。所以我们可以定义一个 J， 那是 L plus S， 这样明白吗？
那这里的 L 是小写的 L 还是那个小
L 是 vector operator S 也是 vector operator， 有什么问题吗？这里的 L 如果是半整数的话，对应到的就是 S。
如果是整数，对应到 M。
如果整数的话，它还是 L。这样你明白吗？小的 L 它如果是整数的话，我们还是叫它 L。如果小的 L 是半整数的话，我们叫它 S。这个 L 是指你任何的角动量，它可以不一定指的是轨道角动量，它也可以指的是自旋角动量。但是我们就通称为一个小的 L。可是如果小的 L 它是半整数的话，我们有特别的名字，就叫做 spin。
那它有对应到一个小 m， 那个小 m 是什么意思？
如果 L 是半整数的话，那对应到的 m 是什么？你告诉我嘛，是不是？那它有可能有几种可能嘛？只有两个可能一个是负1/2，一个是正1/2，不是吗？如果 L 是整数的话，那 m 可以等于多少？不是吗 ？L 可以是整数，也可以是半整数。L 是半整数的话，一样这个不等式还是成立，它是介于最大的 m max 跟最小的 m minima。m minima 就是负 L 嘛，不是吗？就是负1/2啊。那 m 最大是1/2，但它每次只能跳一个，不是吗？所以它只有2种可能，一个是负1/2，一个正1/2啊。你如果要把它加在一起的话，你有几个？你可以算这个问题啊，没错啊。J 等于 L 加 S 等于1加2/3。你告诉我有几个？负2/3、负1/2、正1/2、2/3，那是几个？4个。刚不是讲吗？最多的 state 是 2L plus 1，对不对？我管你 L 是整数还是半整数。如果是2/3的话，2乘上 L 加1是多少？2乘上2/3加1是4个，不是吗？如果 L 等于1的话是几个？3个，不是吗？2乘1加1不是这个吗？ This is just a review of a general physics. I suppose that all of you should understand this if you took this general physics 1 or 2, especially this quantum physics. And the mathematical origin of these possible values of m and L come precisely from this derivation that I just showed you. So let's take the last minute to perform this coordinate transformation. So L is a vector r cross gradient in the spherical coordinate, and this gradient is given by this combinations of 3 different operations. Okay, so time is up, but we will continue starting from this coordinate transformations. We will transform this angular momentum operator from this Cartesian xyz to r theta phi in spherical coordinates, and we'll see how easy is it if we simply perform such a coordinate transformation, and which allows us to really get this eigenstates of all these 3 different components of angular momentum operator in this spherical variables.